Now, let us look at what is a red-black tree. A red-black tree is basically a binary search tree which balances itself after every insertion and deletion. But it has an additional property, color. Each node has a color that is black or red. That is why this tree is called as a red-black tree. The main objective is to maintain the balance of the tree after every insertion and deletion. This helps for efficient retrieval and search of data in the tree. Now let us look at the properties which a red-black tree follows. The first property is about the color of the node. The node color is either red or black. The second property is about the root. The root of the red-black tree is always black. It can never be a red node. The third property is an important property. It states that a red parent node cannot have a red child, which means no two consecutive red nodes can come together on a path. We'll look at these properties later. The fourth property is about black property. This states that the number of black nodes in any path is the same, which means while we traverse from a node to its leaf nodes, there will be the same number of black nodes on any path. The fifth property is about the leaf nodes, and it states that the leaf nodes are always nil nodes and they are black. Now let us look at these properties one by one. Now the first property, we can see that each node is assigned a color and they are red or black. Now the second property is about the root. Here we have the root node which is 80 and that is colored black. Now the third property is about the red-red conflict. Here we can see that no red node has a red child. For example, here our node 60 has both the child as black child and 60 does not have any red child. The fourth property is about the number of black nodes. To prove this, let us try to first traverse from the node 80 to node 20. Let us start from the root node 80. It is our first black node. Now we traverse to node 60. The number of black nodes remain the same. Now when we reach the node 25, the number of black nodes increase to 2. We further move to node 20. This side of the tree is fully traversed and we have got 2 black nodes. Now let us check it in another path. While traversing from 80 to 99, let us again start from the node 80. We have got the first black node. Then we traverse to the second node and we have got this second black node in this path. Then we move to its last node. It is a red node. The number of black nodes is 2. In the earlier path also we got 2 nodes. Here also we are getting 2 black nodes, which means this property is satisfied. Now the fifth property is about the nil nodes. We assume that the red-black tree has nil nodes and they are the leaf nodes and they are always black. Let us look at about deletion of a node in red-black tree. In deletion of a node in red-black tree, there are various cases. But here we will be looking at only 3 of them. The first is about deletion of a red leaf node. The second case is about deletion of a black node with only one red child. The third case is about deletion of a black node but with 2 red child. In the deletion of a node in red-black tree, we have to concentrate more on the deletion of black node because this violates the main properties which are followed by the red-black tree. That is, the number of black nodes on any path remains constant. Let us look at the first case, that is deletion of a red leaf. This is the easiest case. We just need to delete the node. No further operations are required on the red-black tree to maintain its balance. This is because a red node deletion and that too a leaf node deletion does not violate the black property. So let us look at an example. In the example, we have to delete node 40. Let us start from the node 8. First step is traverse to the node 40. We have started from the root 8. Since 40 is greater than 8, we traverse the RST, that is the right subtree. We have reached the node 17. We further traverse the node. Since 40 is greater than 17, we again traverse to the right subtree. We have reached 25, and now we have reached the node 40. Now the step 2 is about the deletion of the node. We just need to delete the node. No further operations are required. Now we can look at this tree and see that this tree is properly balanced. None of the properties of red black tree is violated. Now let us look at the case 2, where we are deleting a black parent node with only one red child. As I told earlier, this deletion requires special attention because deleting a black node actually decreases the number of black nodes in that path, which is not good. It does not follow the property of a red black tree. So we have to do some changes. We'll look at those changes in the later steps. So the first step, as usual, we have to traverse to the node. Then we have to replace the black node which needs to be deleted with its only red child. And after replacement, we have to recolor the black node. Now let us look at the example. We have to delete the node 25. So first we traverse to the node 25 and we start from the root node 8. Since 25 is greater than 8, we traverse to the right subtree. Now again we traverse to the right subtree and the node is reached. Now we need to delete this node 25, which is a black node. The second step states that we need to replace the node with its only red child. Now we will replace its child 18, and after replacement we can see that there is a red conflict. That means the 17 is a red node and it has a red child, that is 18, which does not follow the property of red black tree. So we need to change the color of the node 18, and now this node 18 will become black node. If we see, there are still 2 black nodes on any path. Now let us look at the third case, where we are deleting a black parent node with 2 red child. Here the steps are similar to deletion of a black parent node with 1 red child, but with just one extra step. That is, we need to swap it with its in-order predecessor or in-order successor. Now what are these? In-order predecessor is the element or is the node which comes right before the target node while doing an in-order traversal. And in-order successor is the node which comes right after the target node during an in-order traversal. In simple words, it can be stated like the largest element in the left subtree. The largest element in the left subtree is the in-order predecessor, and the smallest element in the right subtree is the in-order successor. So during the in-order traversal of this tree, we can see that first we traverse to node 2, then 5, 6, 8, 15, 17 and 18. So for example, if we look at the in-order predecessor and successor of node 5, we can see that the element which is traversed before node 5, that is 2, is the in-order predecessor, and node 6 is the in-order successor. Now let us come back to the cases. Now after we have swapped it, we have to delete the new leaf node and we will check whether the properties are satisfied. Usually it is not satisfied, and when it is not satisfied, we just need to change the color as we did in the previous case. Let us look at the example. we have to delete the node 5. So we have to traverse to node 5 first, and we start from the root node 8 as usual. Then since 5 is less than 8, we traverse to the left subtree. Now we have reached the node 5. Now the step 2 states that we have to swap it with in-order successor or predecessor. Here I am swapping it with its in-order successor. As we saw earlier, the in-order successor of 5 is 6. So we will just swap it with 5 and 6. After this swap, we just need to delete the node 5, which was the original black parent node, but now it is a leaf node. So we just need to delete the node 5. Now we can see that the properties are violated, since 6 is a red parent node and 2 is a red child node. Now what we will do in this case, we just change the color of the node which replaced the black node. That is, we'll change the color of the node 6, which was red, to black.